Wow, my mic was off. Sorry about that. Let me know if you can hear me now. Hold on, let me double check OBS. Yeah, it's looking like there's audio coming through now, so my bad. In any case, so the purpose of this video is to add up the Fibonacci series, right? So it's a series that looks like this. Actually, why don't I write it without a summation symbol? So the terms of the series are the Fibonacci numbers. So, what are the Fibonacci numbers? It's like 1, 1, 2, 3, 5, 8, 13, 21, and so on, right? And so the idea is that, you can construct a series out of this, get 1 plus x plus 2x squared plus 3x cubed plus 8x to the fourth plus 13x to the fifth, and so on. So maybe if you just love series, you might, independent of any application, be interested in what the sum of this series is. And actually, being able to answer this question helps you understand the series. It helps you, solve recurrences, okay? It helps you come up with explicit formulas for recurrences, which is extremely interesting. But I'm going to motivate this by something we've talked about previously, which is kind of interesting. So, do you guys remember the question about the expected wait time for a heads versus a heads-tails? So we talked about this last time. It turns out that if you flip a fair coin, right? If you flip a fair coin, the amount of time you have to wait for a heads is longer than the amount of time you have to wait for a heads-tails. So if you just keep flipping a fair coin over and over again, it turns out, and we analyzed this using a martingale last time, which is a very fancy trick. We're going to do more down-to-earth stuff this time. So we figured out the expected wait time, or the number of flips you have to wait for heads is 6. And the number of flips you have to wait, the expected number of flips you have to wait for a heads-tails is 4, which in itself I think is very interesting because I remember the first time I ever thought or heard about this, I found it extremely counterintuitive that you would have to wait longer for a heads than a heads-tails. And so if you're anything like me, maybe you found it counterintuitive as well. But we analyzed this and we were able to figure out the answer using martingales. But let's say you're not so fancy, you don't know about any of that stuff. You don't know you have no idea what a martingale is, okay? What are you going to do in that situation? Well, in that situation, you have to appeal to the definition of expected values. What is an expected value? So in this case, we're interested in the expected wait time, right? So expected value. So in this case, we're interested in the expected wait time for a heads versus the expected wait time for a heads-tails, okay? So the expected wait time for a heads versus the expected wait time for a heads-tails. How do you compute expected anything? Like, how does that work? How do you compute expected anything? Well, the idea is pretty simple. You write down the possibilities, and then you write down their probabilities. And then you just add them up, right? You just multiply every possibility by its probability, and then you add the whole thing up, okay? So in this case, though, there are actually infinitely many possibilities in either case, okay? So let's think through the possibilities for getting a heads-tails first, because that's the easier situation to analyze. So how many situations are there where you get a heads-tails in a certain number of flips? So the possibilities in this case are, you have to wait a certain number of flips. You certainly can't get a heads-tails in one flip, right? Heads-tails itself takes 2 flips, but you could get your first heads-tails in 2 flips. You could get your first heads-tails combination in 3 flips. You could get your first heads-tail combination in 4 flips, right? You could get it in 5 flips, and so on and so forth, okay? So these are the possibilities here. Now, in order to analyze their probabilities, and remember, we're taking a more kind of humble, down-to-earth approach here, let's just analyze the probabilities here just by, writing out all the different ways you can get heads, tails. Okay. What is the probability of getting a heads, tails in just 2 flips? What is the probability of getting heads, tails in just 2 flips? Well, if you wind up getting a heads, tails in just 2 flips, what does that mean? That means the first flip you got a heads, and the second flip you got a tails. That's a 1 in 4 chance of happening, okay? This is a 1 in 4 chance of happening, okay? Now, what are the possibilities that lead you to a heads, tails in 3 flips? Well, there are 2 situations where this can happen. You can get tails, heads, tails, or you can get heads, heads, tails, right? These are the only 2 possibilities that exist where the first heads, tails you encounter is in the last 2 flips. Hopefully that makes sense. There are 8 total possibilities for 3 flips. So the probability of getting your first heads, tails in 3 flips is going to be precisely 2 out of 8. Does that make sense? All right. What is the probability of seeing your first heads, tails in 4 flips? Well, hopefully the pattern is simple enough that it's clear. If you see your first heads, tails in 4 flips, well, how many ways can that happen? Well, you could have heads, 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 tails. You can have tails, heads, heads, tails, or you can have tails, tails, heads, tails. So there's 3 possibilities, right? Where you see your first heads, tails in 3 flips, and that's 3 out of 16. So the probability here is 3 out of 16, okay? And once again, I hope the pattern is clear. For the number n, it's just going to be n minus 1, I believe, over 2 to the n. Let me know if I've made any mistakes, and please let me know if there are any questions here. There's a slight delay, so I'm just going to start talking about the next thing. Though, if someone does have a question, I will I'll pause to answer it. But it's okay. So these are the possibilities, and these are the probabilities. So it turns out if you are interested in computing the expected wait time for a heads tails, the series that you have to sum is the following. Actually, I don't know why I erased that. That was very useful. The series you would have to sum is you multiply each possibility by its probability, right? And add that up. So if you are interested in the expected wait time for heads, tails, it would be the sum of the following series. It would be the sum of n times n minus 1 over 2 to the n. As n goes from, I guess, 2 to infinity. Okay, this is very important. So let me know if this here makes good sense to you. So it's n times n minus 1 over 2 to the n. This would be the series that we would have to sum. Are we sure the possibilities are not n minus 1 factorial over square root of n? You might have to explain a bit more how you got that. I'm not sure. So the way I see it, so the only way, so if you want a heads tails at the very end, right, then essentially you can start out with a sequence of tails. This could be a sequence of length 0, and you have to have a sequence of heads after that. And the only real decision that you have to make is where the tails switch to the heads. Nathan, I want to say it's not an issue of intelligence. These videos are directed for people who are like maybe starting out in their college math careers or at the end of their high school math careers. So I don't want you to be discouraged. At the end of the day, I have to pick a target audience, and the target audience is going to know some things and is not going to know other things. I do my best to cater to everyone, but please don't be discouraged. Okay. Hello, Ken. All right. So let me know, Jamie, if that makes sense. So in order to have a heads tails at the very end, you can have a sequence of tails, and then it has to stop, and then you have a sequence of heads, right? Ending in a heads tails. That's pretty much the only way you can set things up so that the first heads tails you encounter is the very end. So essentially the only decision you make is where this line is, like where the tails, thank you so much, Nathan. So the only decision you can make is where these tails eventually turn into heads. And so there are basically end decisions about where you can make that, and so that's why that's why the probabilities look like this. So let me know if that makes sense, Jamie, and so I'm going to move on. So the idea is that in order to figure out the expected wait time to see a heads tails, I would have to add up this series, n times n minus 1 over 2 to the n. Okay? This series is, if you remember the end of your calculus classes, yes. You have to be careful about that. You have to make sure the first heads tails you see is at the very, very end, right? So this is fundamentally the series that we're summing up. We're summing up the series n times n minus 1 over 2 to the n. Now, there's a classic kind of standard, calculus-y way to do this, and you just do the following. So what you do is you figure out what's going on with the series n times n minus 1 t to the n, right? Where n goes from 2 to infinity, right? So you figure out what's going on with this series, right? Maybe this is the Taylor expansion of something, okay? It's not best to always think about Taylor expansions, but the correct methodology to think about this is generating functions, because the minute you start thinking about Taylor expansions, you have to worry about whether or not they converge. But you'll notice in this video, I'm just simply not going to care about whether or not stuff converges. So I want you to know this is legal in the context of another type of mathematics called generating functions. However, Taylor series are a great way to get your feet wet with generating functions. So here's my master plan for figuring out what this series sums to. So I need to figure out the sum n equals 2 to infinity of n times n minus 1 over 2 to the n. Why don't I figure out what the heck is going on with n times n minus 1 times t to the n? And once I know what function this is, I can plug a 1/2 into this function and be done. I can walk away from this. So let me know if that approach, if that style makes sense. Okay. So, as with a lot of problems that involve kind of Taylor series style shenanigans, you don't want to use the formula for Taylor expansions. You want to start with one that you know and then manipulate it to get the one that you are interested in. Okay? So one that I know, one that I like, let me move this up top. So hold on. Okay. Here's an expansion I know, and it's okay. Ken, like math is, in math when you teach, you only present the results. You don't represent the misery of the people who come up with them. So everything just seems like clairvoyant, insane magic, when you see it like this. But keep in mind, the things that I'm talking about represent significant effort. The perspective I'm about to describe represents significant effort on the part of a lot of people. So let's not let's not forget about that. But Okay, so I'm adding up this series, and so I just need to figure out what's going on here. Here's a series I know, which I like. So 1 plus t plus t squared plus t cubed plus, go on forever. Now, if you remember, this is 1 over 1 minus t. Once again, this equality only holds true if the absolute value of t is less than 1. But in this video, we're not worrying about convergence at all for reasons that I am not explaining. But you get that, the expansion of 1 over 1 minus t is 1 plus t squared plus t cubed, and so on. Let me know if you remember this particular expansion. If you don't, think back to the sum of a geometric series. And if you don't remember even that, multiply both sides by 1 minus t and see what happens. Okay? Just if you multiply, and once again, this is like a weird, purely theoretical thing where I'm not worrying about convergence whatsoever. But if I multiply both sides of this by 1 minus t, you'll get that 1 equals 1. Okay? So 1 over 1 minus t is equal to this expansion over here. Let me know if that makes sense. Also, let me know if you want me to multiply both sides by 1 minus t. I'd be happy to pause and do that for you right now. But regardless, this is 1 over 1 minus t. Okay, now this series here, what does it look like? It looks like, let's see, 2 times t squared plus 3 times 2 times t cubed plus 4 times 3 t to the 4, and so on and so forth. Let me write the first term as 2 times 1 t squared, and so on and so forth. So how do we get this one to look more like that one? I mean, that's the one we're interested in, right? Can we multiply first? You can multiply. Would you like me to multiply this so you can see it? Yes, absolutely. So if I multiply both sides by 1 minus t, first think about multiplying it by 1. If I multiply it by 1, I get 1, the same thing back, right? 1 plus t squared plus t cubed, and so on. If I multiply it by minus t, I get, think about that, it would become minus t squared minus t cubed minus t to the 4th, and so on. And so notice everything cancels out except for the 1. Okay? So if you multiply both sides by 1 minus t, you just get 1 equals 1, which is a way of justifying this formula in case you've never seen it before. But keep in mind, if you want to plug in numbers like we're going to do, this formula only makes sense when the absolute value of t is less than 1. If the absolute value of t is greater than 1, the sum on the left-hand side diverges, like it just blows up. Because you're adding t to t squared plus t cubed and so on and so forth. So that blows up. So let me know, Jamie, if that makes sense. Multiplying 1 minus t on both sides gives us that 1 equals 1 on both sides. Okay. So now we would like this thing to look like this thing up here. We would like this thing to look more like this thing. Okay? So how do we get this thing to look more like this thing? Well, I have an idea, assuming no one else has an idea. Maybe I should wait a second to see if anyone has ideas about what to do. How do I get this thing to look more like this thing? The idea is that here's a series that I do know the sum of. I'm trying to get a series that I don't know the sum of. Can I massage the one I know to get something that I do not know? Right? That's the question. I did not know you could do that with Taylor series. You cannot do that with a Taylor series. You can only do it with Taylor series if you don't worry about convergence, right? You can only do that with Taylor series. Is this something like the proof that 1 plus 2 plus 3 is negative 1 over 12? That's a whole nother thing, okay? This is a lot more, this is much more working class mathematics. That's like very, very fancy. Well, we can talk about that someday. But yes, Hitoshi and Double Bread Black Hat gave the correct answer. I can differentiate both sides, okay? In fact, if I differentiate both sides twice, and Jabubu, you're correct as well. So if I differentiate both sides of this equation twice, it will actually look exactly like the series above. So let's differentiate this once. Okay. So if I differentiate this once, the left-hand side will just become, the 1 vanishes. So I get t plus 2t squared plus 3t, plus 2t plus 3t squared plus, and so on. And this equals the derivative of 1 over 1 minus t. What's the derivative of 1 over 1 minus t? Well, this is 1 minus t to the negative 1, right? So it'll be 1 over 1 minus t quantity squared. Let me know if I make any errors differentiating. I'm unfortunately very prone to numeric errors. So yeah, it's my Achilles heel doing mathematics is numerical errors. I make them constantly. So just to warn me if that's the case, but if you differentiate both sides, this is 1 minus t to the negative 1, should be negative 1 minus t to the negative 2 times negative 1. So I think the negative should cancel, and you get 1 over 1 minus t squared. You know what? I'm just going to open Mathematica and verify it, because I just don't trust myself, you know, having done math for so many years. Let's see. So the derivative, also doing it live is a little, you know, it's a little nerve-wracking. So I'm just going to differentiate it. Okay, it's correct. It's 1 over 1 minus t squared. That was correct. Okay. Now let's differentiate this one more time. If I differentiate it one more time, the left-hand side becomes 2 plus, and this is going to be 3 times 2 times, whatchamacallit, t plus, you know, 4 times 3 t squared, right? Running out of room, so I'm just going to have to erase some of this stuff. I'm just going to erase this. Okay. So this is, okay, so now I need to differentiate this thing. This is 1 minus t to the negative 2, which should just be 2 over 1 minus t cubed. I'm just going to double check that with a calculator real quick. So yes, I was correct. So this now, if you look at this, this is looking very close to what we had up top. Let me just show you this up here. It looks indeed very close to what we had up top. So move it up. And there we have it. Okay, this looks, oh, cancel. This looks very, very close to what we had up top. And I believe someone else has already given the answer. If I multiply both sides by t squared, they will be identical to each other. Okay, I believe it was Double Bread Black Hat that gave the correct answer. So you just need to differentiate twice, and you multiply both sides by t squared, and now both of these are the same. So hopefully that makes sense. So it turns out, so if you multiply both sides by t squared, you'll get 2t squared plus 3 times 2t cubed plus 4 times 3t to the 4th. And you notice this is now identical to the 1 up top. And this is equal to now 2t squared over 1 minus t cubed. How interesting. Okay? So we get that this series, we have our answer. Where it converges, and once again, I'm eliding all convergence considerations, but where it converges, it should equal 2t squared over 1 minus t cubed. So this is 2t squared over 1 minus t cubed. How interesting. So remember, what was our original goal? Our original goal was to compute this sum, right? N times n minus 1 over 2 to the n. And we can, of course, do that by plugging 1/2 into the identity that we figured out above. How interesting. So this should equal 2 times 1 over 2 squared, 1 minus 1 over 2 cubed. So This is 2 over 4, which is a half, divided by a half cubed, which is an eighth. So this is 4. What do you know? The expected wait time for a heads tails is exactly 4, which is exactly what we figured out using martingales like 2 videos ago. Okay, so I hope you can see the application of series to figuring out probability questions in this situation. Okay? Let me know if there are any questions about this, and if not, let's analyze the much more interesting situation of the expected wait time for a heads. Okay? That situation is significantly more interesting because this series was not, I had to just compute a couple derivatives and we were able to figure out the series. Okay, but the other one is going to be a little more spicy. So let's if there are no questions about this, I'm just going to dive into that one. So we've figured out the expected wait time for a heads tails is 4, right? Now we know from an argument that I gave 2 videos ago that the expected wait time for a heads is going to be 6, and of course. Good question here is, how is that going to happen? Well, let's see here. Once again, we take the same approach. We're going to take a very kind of pedestrian approach. We're going to write down every possibility and every possibility's probability. Okay? We're going to multiply everything, add it up, and that is how we are going to figure out what the expected wait time is for a heads. Okay. Possibility, probability. Okay. This time we are analyzing for heads. Okay. You cannot get a heads before you flip twice. And if you do, there's only one way to do it. So at least this starts out the same way. The possibility of getting your first heads in 2 flips has a probability of 1 out of 4. Because there are 4 possible sequences of 2 flips that you can have, right? There's 2 possible sequences of, there are 4 possible sequences of 2 flips that you can have, and only one of them is a heads. Okay, let me ask you guys next. What are all the different ways that you can have your first heads appearing in 3 flips? It turns out here there's only one way that this can happen. Tails, heads. This is the only possibility that allows your first heads to appear in the last 2 flips. You can check, I'm not lying to you, this is the case. So this is going to be 1 out of 8. Okay? Hopefully that makes sense. Let's do it for 4. Let's do it by hand at first, and then there's something going on here which I'm sure you'll figure out soon enough based on, well, I won't say it. So what is the how many possibilities are there where you see your first heads on the last 2 flips and no heads prior to that? Well, let's think about it. So you could have a heads-tails situation, right? You could have a tails-tails situation. And this is it. These are the only 2 possibilities in 4 flips, which will allow you to see a heads on the last 2 flips. Okay? Aha. So this is 2 out of 16. All right? Let's do 5 now. What are all of the possibilities where you see heads at the very end? Not 3? What would be the 3, Hitoshi? Let's see. So my claim was that the only ones were heads, tails, heads, and tails, heads. What are the others? Ken, I'm not simplifying the fraction for a reason. So I'm just going to leave it as 2 over 16. Okay. So heads, tails, heads, heads, tails, tails, heads, heads. These are the only two. I'm going to try it out. What are the others? Where you see, remember, you have to see your first heads, heads has to occur at the very end, the last set of 2. Okay? So let's do for... yeah, I know. It is interesting that it's not the same situation there. But regardless, let's do for 5. So for 5, I claim that there are going to be 3 possibilities. So there's going to be tails, 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 heads, heads. You could also have heads, tails, tails, heads, heads. But you could also have heads, heads, tails. Oh, no, you can't have heads, heads, tails, because then the heads, heads occurs first. But you could also have tails, heads, tails, heads, heads. Okay. These 3 possibilities are it, so you get 3 out of 32 here. Be very happy with the first person that spots the pattern here. So let's do one more. Okay. So I claim for the next one there are going to be 5 possibilities. There are 5 ways you can see heads, heads at the very end of 6 flips. And what are they? Let me write them out so you can have tails, heads, heads. This is at the very end. Let's see. So you could have all tails. So tails, tails, tails. You could have heads, tails, tails. You could have tails, heads, tails. You could have tails, tails, heads. What else? You could have heads, tails, heads. So these are indeed the only 5 possibilities. And Jamie got it. Good work. So it is 5 out of 64. And what do you know? We are dealing with a Fibonacci sequence over here. You see it? 1, 1, 2, 3, 5. Yeah, it's Ken, it's Fibonacci over 2 to the n, not n squared. But you basically have it. So the probability of seeing your first heads heads at the very end in n flips turns out to be the, let's see. So this, I have to say, comes down to how you index Fibonacci numbers. I'll tell you how I index Fibonacci numbers. Just remember, not everyone does it the same way. I put the first Fibonacci numbers F0. Some people start at F1. Hopefully it doesn't make you feel bad or something that I'm starting my indexing at 0. Hopefully no one thinks it's a big deal. So this should be F n minus 2 over 2 to the n is the probability of seeing your first heads heads at the very end of n flips is going to be the n minus second Fibonacci number divided by 2 to the n. How about that? I mean, how many people were expecting that? Isn't that cool? It's very nice. Okay, so in order to figure out the expected wait time to see a heads heads, I need to multiply each possibility by each probability and add the whole thing up. And so now it turns out that the series, so I would have to multiply 2 by a fourth, 3 by an eighth, 4 by 2 sixteenths, 5 by 3 32nds, 6 by 5 64ths, and add the whole thing up. Okay? So the series I now need to add is this one. It's the sum n goes from 2 to infinity of n fn minus 2 over 2 to the n. Now I want you to note this is actually even nastier than the one I put in the thumbnail. But first, before we go on here, I want to ask you guys, how might you prove that hello, Lloyd. How might you prove that I was right about the Fibonacci thing? I mean, just because you see the first couple Fibonacci numbers, that's not a proof, right? What's going on here? How do we know that the number of possibilities of seeing heads at the very end of n flips is the n minus second Fibonacci number, assuming you index them like I do? If you index them the other way, it's the n minus first Fibonacci number. Okay, so why? Why? Any ideas? Any ideas as to why? Any comments or conjectures as to why that might be the case? I'll actually wait a minute. I'm curious to see how intuitive people find this. Anything at all? You know, it is indeed surprising where Fibonacci numbers pop up, but why did they pop up here? What is going on here? Probably wait for like 10, 20 more seconds and then continue on, if no one has any idea. It involves the patterns. 2 before strings concatenation. Almost, Hitoshi. You are very close. So double-bred black hat, it does indeed involve the patterns, but what pattern specifically? It has to do with the flip-flopping of the heads as you add more flips to the beginning. Okay. Proof by induction that the permutations of n sequence, some of the prior to, the previous pattern repeats in the next iteration. You are all very close to the correct answer, but I would like to prove it because it's good. It's good to look at it. This pattern or like various recurrences pop up in life, and it's good to know how to be able to prove the recurrences, so you can write a neat and tidy proof whenever it comes up. So this won't take too long. I want to actually prove it for you. Okay, so let's say you flip. So I want to say about double-bred blackhead's answer. It's not quite that the previous pattern repeats in the next iteration. You're close, but that's not 100% correct. So let's say you have a sequence of n flips, right? Where the last thing that you see is heads. Okay? You have a sequence of n flips where the last thing you see is a heads, and on no prior flip, there's no heads anywhere before this, right? That's essentially what we are interested in. Right? There can be no heads occurring before this. Well, let me tell you, I know one thing for sure. That means this has to be a tails, right? If this are a heads, then a heads appeared prior to this, right? Like, that doesn't make any sense. So that the flip before the heads has to be a tails. If it were a heads, then you have a heads appearing before the final heads. Make sense? Okay. And what sort of shenanigans are going on here? It's a good question. What sort of shenanigans are going on here? Well, inside here has to be a sequence with no heads in a row, right? No heads in a row. That's right? So no consecutive heads is what has to be filling this question mark space. Right? So this thing has to be, some sequence can be any sequence, no heads in a row. No neds, good work. No heads in a row. Hopefully this makes sense. And by the way, whenever you take your discrete math class, you'll have to prove recurrences. And the things that I'm about to do it's like the strategy you generally use to prove recurrences in your life. Okay? So what goes in here is no heads in a row. Okay? I'm going to split this. So this is a sequence of length n minus, 3 with no heads in a row, right? This is a sequence of some length. I'm going to call it M, right? A sequence of length M with no heads in a row. Okay? A sequence of length M with no heads in a row. Okay, cool. There are two possibilities for such a sequence. Either this sequence, the one inside the oval, either it ends in a heads or it ends in a tails, right? Those are the two possibilities. Okay. So I'm going to split the types of sequences that go in here into sequences that either end in a heads or end in a tails. So this is going to be end in a tails or end in a heads. Hopefully that makes sense. So you can either end in a tails or you can end in a heads. Okay. If you end in a tails, so now I'm once again, I'm analyzing only the things that appear inside this oval. But if you end in a tails, before this, you can actually put in any sequence of length m-1 with no heads in a row. Okay? So sequence of length m-1 with no heads in a row. Okay? Take any sequence of length m-1 with no heads in a row, throw a tails at the end, you will have a sequence of length m with no heads in a row. Hopefully I'm not blowing anyone's mind. Hopefully this makes sense. If you take any sequence of length m-1 with no heads in a row, you throw a tails at the end, you will get a sequence of length m with no heads in a row. Okay. But here's the thing. If it ends in a head, then the flip before it has to be a tails. If you have a heads here, you're canceled because heads, heads, tails, heads, heads, bad news, right? So you know for a fact that if you end in a heads, you have to put a tails before the heads. But then before that, you can put in any sequence of length m-2 with no two heads in a row. So any sequence of length m-2 with no heads in a row. And there's the Fibonacci. The sequence of length m with no heads in a row splits into the sequences of length m-1 and m-2. So whatever this number is, if I call it a sub m, it turns out a sub m is the sum of a sub m-1 and a sub m-2. And that there is why the Fibonacci sequence is occurring here. And keep this strategy in mind for solving recurrences in your future. Let me know if there are any questions about that. Let me know if it makes perfect sense. Okay. And if not, we can dive into adding up this series. Okay. Any questions about this? Okay, I'm going to assume not, because once again, there's a delay, and then we can dive into adding up this series. Okay, this series is a bit harder. Let's start by thinking through. Oh, by the way, our strategy is exactly the same. In order to figure out what the sum of this series is, we're going to think about this function. We're going to think about n 2 to infinity, the function n fn minus 2 t to the n. And if we can happen to figure out what this function is, we can plug out 1/2 into that function, and that will give us our answer. Okay? Barring convergence issues, which once again I'm not talking about very carefully in this video, hopefully the strategy makes sense. It's pretty much the exact same strategy that we used for the previous one. It's just a more complicated series. Before we kind of dive into any of this, let's focus on a slightly simpler series. Let's just do the series that's in the thumbnail. If we can do the series that's in the thumbnail, We should be able to do this more complicated one. Okay, so let's just do the one in the thumbnail. The series in the thumbnail of this video is the sum n goes from 0 to infinity of fn t to the n, which is, by the way, just like, 1 plus t plus 2t squared plus 3t cubed plus 5t to the fourth, and so on. So, yes, Ken, if you already know about generating functions, this is exactly what we are about to do. We are about to derive the generating function for the Fibonacci numbers. Okay. So, I'm adding up fn tn, which is 1 plus t plus 2t squared plus 3t cubed plus 5t to the fourth. This is the series in the thumbnail. Let's figure out what's going on here. Well, I'm going to call this function like capital F of t. Okay. I'm going to call this function capital F of t. Okay. The idea is that if I can figure out this one, it should give me some angle on how to deal with the more messy one up top. Okay. So this is f of t. It is equal to this. Okay. So let's work through this. Here's what I'm going to do. I'm going to think about what t times f of t is. T times f of t is going to be like, things get shifted. So it's going to be like t plus t squared plus 2t cubed plus 3t to the fourth, and so on. So what I'm doing is, I've shifted all. So now the coefficient of t to the n here is the previous Fibonacci number instead of the same Fibonacci number. Hopefully that makes reasonable and perfect sense. So, but now what I'm going to do is add these. Okay? What happens if I add these? Well, if I add the left-hand side, I get 1 plus t f of t. And this will become like 1 plus 2t plus 3t to the squared plus 5t cubed plus 8t to the fourth. Another Fibonacci sequence. Okay? So 1 plus t times f of t becomes 1 plus 2t plus 3t squared plus 5t cubed plus t to the fourth. Hopefully, all of this makes sense so far. I need to move this up a bit because I'm just always running out of room. Okay, so let's transform this. Let's move it up. Done. All right. Okay, this is looking pretty good. I'm going to take this 1 just because. See, what do I want to do here? Well, this is very close to the series that I started with, right? Actually, why don't I multiply both sides by t? Okay, so I'll multiply by an additional t. So this becomes t plus t squared times f of t equals now t plus 2t squared plus 3t 3t cubed plus 5t to the fourth, and so on. So now you notice this line here is only 1 off of the original line. Do you see that? Except for this 1 at the front, this line and that line are exactly the same. Notice, by the way, we use the recurrence of the Fibonacci numbers in order to figure this out. So you get, 1 plus 1 is 2, right? 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on, right? So apart from this 1, this line is the same as the first line. So you know what I can do? I can write it like this. T plus t squared f of t is equal to f of t minus 1. Because it's the same as the first line, except for the 1. Okay? Hopefully that makes sense. So let's finish this up. Let's put all of our, so we have this very interesting formula now, right? Which is that, if I put all of my f of t's on one side, I'll just get ft, right? Which was the series whose coefficients were the Fibonacci numbers, is equal to 1 over 1 minus t squared. Not equals 0, just equals f of t. Because you just put all the f of t's on one side and then you divide. And so it turns out that the compressed form of the series, whose coefficients are all the Fibonacci numbers, is just 1 over 1 minus t plus t squared. Interesting, right? Let me know if there are any questions about that. I want to say to you that this is an absolute gem of a formula, okay? You can actually use it to derive a closed form solution for all Fibonacci numbers. So it will actually give you, if you stare at it for long enough, a formula for the nth Fibonacci number that does not involve computing the previous Fibonacci numbers. If you're interested in that derivation, and I'm almost running out of time, so I don't want to do it in this video, what you would do is you would think about what are the roots of 1 minus t squared, okay? You'll notice that the roots of this are, 1 will be the golden ratio, 1 will be its, so 1 will be like 1 plus root 5 over 2 will be one of the roots, which is the golden ratio, by the way. It's the limit of the ratio of the Fibonacci number. So of course it's interesting that that shows up here. And then the other one will be 1 minus root 5 over 2. Those will be the two roots of this polynomial, okay? Either that or they're negatives. I am blanking right now. But you factor it like so. You do 1 over t minus, I guess you would write like phi minus t, phi, like psi minus t, where one of them is 1 plus root 5 over 2, the other is 1 minus root 5 over 2. And then you can use partial fractions to split this up. And that gives you the closed form solution for the Fibonacci numbers. Let me know if you want to see it. I can do it. But I don't want to get too far off our topic here, which is figuring out the expected wait time for heads. Okay? So this series is just, let me write it in. So this one is, if you were to add up like 1 plus, why don't I write it with like coefficients? So it would be like, this is like f0 plus f1x plus f2 x squared plus f3 x cubed, and so on. Okay? That is what this is. What we are interested in is the following series. Let me write down the one we're interested in. We're interested in this one. We're interested in like 2 f0 x squared. Actually, I don't know why I'm using x's on the left-hand side and t's on the right-hand side. I think it's probably faster to switch the... Sorry about that. 2f0 x squared would be the first term here, plus, I guess, 3f1 x cubed, and so on. This is the one we're interested in. Okay? Let me know if there are any questions about that. This is the series I would have to sum up in order to figure out what this sum is. So the idea is, of course, in order to figure out what this is, I'm figuring out what this is with a t to the n here. And then at the end, I'm going to plug in t equals 1/2. So how am I going to figure out what this is? Well, we did the hard work already. Like, we figured out the hard one. And so we just need to manipulate this one in order to figure out this one. Okay? So here's what I'm going to do for the sake of ease and comfort. I'm going to call this one gx. Okay? G of x is our unknown. It is the one that we are interested in. It's the one that we want to solve for. Okay. The first thing I note about it is that it's off a little bit, right? It's the indices of the Fibonacci numbers don't really match up with the indices I have up here, right? So the first thing I'm going to do is I'm going to divide by x, okay? What is g of x divided by x going to be? Well, it gets me closer. So now I have 2f0 x plus 3f1 x squared plus ... and so on. Let me know if that makes sense. So g of x over x is 2f0 x plus 3x squared. Now you might recognize like 2x, 3x squared, and so on. These are just the derivatives of the powers, right? And so if I just integrate gx over x, ignoring the integration constant, another talk for another day about what exactly happens to it. But if I just integrate gx over x, I would get f0 x squared, right? Plus f1 x cubed plus f2 x to the fourth, and so on. Let me know if that makes sense. Okay, so we're very close now. We're very close to home. Sorry I have to like erase old stuff, but so we have g of x over x is equal to this. This is very close to the power series we had for the Fibonacci numbers, right? It's off because there's like, the indices are off just a little bit. But you know what I can do? I can just take the integral of g of x over x and divide it by x squared. And now I have on the money exactly f0 plus f1x plus f2 x squared plus ... Okay? Hopefully that makes sense. So f0 plus f1x plus f2 x squared plus, and so on and so forth. All right. What is this? This is capital F of x. Exactly, right? This is exactly the series we had for the Fibonacci numbers. So it turns out this is just 1 over 1 minus x squared. How neat is that? That's very nice. So we have this. And so the integral of g of x over x is x squared over 1 minus x squared, right? Okay, fantastic. Now I differentiate both sides to get rid of the integral. So we get g of x over x is, we have to do the, the quotient rule, right? It's like 2x, 1 minus x squared, and then minus 2x minus 1 x squared divided by 1 minus x squared, quantity squared. Please let me know if I messed that up at all, though it'll show up because we'll get the wrong answer at the end. So g of x over x is equal to this. There should be some nice cancellation that happens here. So let's see what happens. So g of x over x is now equal to I guess, 2x minus 2x squared minus 2x cubed plus 2x cubed plus x squared divided by the denominator, which is 1 minus x squared, quantity squared. We're almost home. And so this is equal to, so the 2x cubes cancel, so you get 2x minus x squared over 1 minus x squared, quantity squared. Now you just multiply both sides by x, and you get g of x is equal to 2x squared minus x cubed over 1 minus x squared, quantity squared. And I just wanted to do this out so you know how to deal with something like this if you happen to encounter it in real life. Okay? So, hey, what do you know? We have our thing. So this thing is equal to 2x squared minus x cubed over 1 minus x squared, quantity squared. Let me write that in before I erase everything. So this is equal to 2x squared minus x cubed over 1 minus x squared, quantity squared. And once again, I'm using t's on one side, x's on the other. You'll have to forgive me. You just now need to plug in 1/2 and walk away. So this becomes the sum. If you plug in 1/2 on both sides, it becomes n fn minus 2 over 2 to the n equals, plug in 1/2. So 2 times 1/2 squared is 1/2 minus 1/8 divided by 1 minus 1/2 minus 1/4 quantity squared. So what's the numerator going to be? It's like 4 over 8 minus 1 over 8. So the numerator is looking like a 3 over 8. 1 minus 1/2 is 1/2. 1/2 minus 1/4 is 1/4. 1/4 squared is a 16th. So this is 6. What do you know? The exact answer that we got using martingales in like 2 seconds, we were able to get using this method in an hour. Totally worth it. No, I'm just kidding. So the point of this was to teach you how to deal with series that you might encounter like this. And I don't know what to say. I hope you liked it. Thank you, Jabubu. Thank you. I think that's all I have to say for today. Let me know if there are any parting questions. Please look up the Binet formula for Fibonacci numbers. You can derive it from the fact that the so-called generating functions for the Fibonacci numbers are 1 minus t squared. Or if you would like a fun exercise on your own, derive a closed form for the generating function. I'm sorry, a closed form for the Fibonacci numbers. By the way, by a formula for the Fibonacci numbers, I mean a way to compute the nth Fibonacci number without computing the previous Fibonacci numbers. Okay? And the way to do that is split this up using partial fractions. If you've taken calculus, you should remember some partial fractions, hopefully. Thank you so much, Foolish. I appreciate it. And, there it is, 6. So if there are no more questions, and if you want to do more, think about the Binet formula on your own. I don't know. I'm trying to think about what to do next stream. I actually found a really good derivation of E equals MC squared. Like, that's appropriate for someone like ending high school, beginning college, kind of like that level. So I think that could be a lot of fun. But I don't know. I think more people show up on Saturdays than Wednesdays, so I might save the E equals MC squared for a Saturday. Let me know if you have any preferences in that regard. And other than that, I think that's all I got to say. So that's it out of me. I will see you again, those of you who can appear on Wednesday at 1 p.m. Eastern time in the United States. I don't know what that is, like GMT wise. But thank you all for showing up. I don't know. I love this kind of stuff. It's a lot of fun. There's so much you can do with this kind of stuff. And right, that's it out of me. So I just want to say peace. Love you all. Thank you. And bye-bye. Let's see here.